Good morning, everyone. I am Dr. Saurabh Datta, Assistant Professor in the Department of Chemistry of Benware University. Today, I am going to discuss another important topic of chemistry, that is the band theory of solids. But before studying band theory, we have to know about the basic concept of MO or molecular orbital theory. Okay, so this is very important. Suppose you have to know how high, for very simple example, I have taken here the formation of the hydrogen molecule. How hydrogen molecule is formed? Hydrogen molecule is formed two hydrogen atom. So each hydrogen atom contain one electron in the 1s orbital. Okay. So these orbitals are called atomic orbitals. So these orbitals are called atomic orbitals. These are the atomic orbitals. This one is and this one is. When these two atomic orbitals are combined, according to molecular orbital theory, they form two molecular orbitals. One is comparatively lower in energy with respect to this atomic orbital, that is called BMO or bonding molecular orbital, and another is comparatively higher in energy with respect to the atomic orbital. So this is called ABMO or anti-bonding molecular orbital. So from this we can say that if two atomic orbital combine, then two molecular orbitals are formed. Okay, so if n number of atomic orbitals are combined, then n number of molecular orbital will form, and between this n by 2 will be the BMO and another n by 2 is the ABMO, anti-bonding molecular orbital. So normal H2 molecule is okay, there are only two hydrogen atoms. But if I am talking about a metal, okay, if I am talking about a metal, there are very much amount of atoms are there. We can say in the order of 10 to the power 20 atoms are there. So if this 10 to the power 20 number of atoms are combined, they also form 10 to the power 20 molecular orbitals, right? And between these 10 to the power 20 molecular orbitals, the half will be the BMO and another half will be the ABMO. Now, those molecular orbitals are too much and they are very close to each other. That's why they almost overlap with each other. So they are appear as a band. They are appear as a band in spite of discrete energy level. Suppose some energy level, if they are very closely spaced, the energy level that are very closely spaced, then we cannot distinguish them. They basically appeared as a band. Okay, so for metal, in this way bands are appears. Now if I talking about a simple example, suppose we are considering a alkali metal like lithium. Okay, so every lithium, what is the electronic configuration? Lithium is 1s2 2s1, right? So which one is the valence shell? 2s is the valence shell. So this contain one valence electron. Okay, so if Li4 molecule is formed, then each lithium atom contain 1 electron in the 2s orbitals. So there are total 4 number of 2s orbital coming from each lithium atom, and they are combined. So 4 atomic orbitals obviously combine 4 molecular orbitals. 2 will be BMO and another 2 will be the ABMO. Now there are total 4 electrons. So they are filled according to the Aufbau principle, following Aufbau principle, Hund's rule, and Pauli exclusion principle. So 1, 2, and 3, 4. So the BMO, that's are basically electronically filled, and there are total 4 electrons. All are present in the BMO. So obviously the ABMO is vacant. There are no electrons in the antibonding orbitals. This is for Li4. Now if n number of lithium atoms are combined to form LIN, then what happened? There also will be n number of molecular orbitals, and n by 2 will be the BMO. That are, this n value is very large, so this BMO will be very closely spaced, so they appear as a band. They appear as a band where all the BMO are electronically filled. Okay, so BMO, the bonding molecular orbital, will be electronically filled, but as Li4, Lin also, the anti-bonding orbital will be electronically vacant. So these BMO and ABMO all are generated from the 2s orbital. So in case of the band of the 2s band, so some portion, that is the electronically filled. So 2s band is not completely electronically filled, it is partially electronically filled, and the electronically filled portion, that is called valence band, and the vacant portion of the 2s, that is basically called conduction band. Okay, where electron is absent. So we all know that 2p orbital is higher in energy with respect to 2s. So in the higher energy, there you also get a 2p band. So obviously in case of lithium, no electron present in the 2p orbital. So after MO formation, 2p orbital also vacant. So this is another conduction band from 2p. But if I talking about 2s, so this is the valence band, that is a partially filled electron is present, and the vacant portion, that is called basically conduction band. Okay. Now the energy gap between valence band and conduction band are called forbidden energy gap. The forbidden energy gap. But in this case, as 2s orbital and 2p orbital, there are almost zero energy gap. So just applying very small amount of thermal energy or electrical energy, this electron can promote it from valence band to conduction band. This electron very easily promoted from valence band to conduction band. Okay, and so these are very much suitable for carrying electricity or heat. Okay, similarly we can explain. So here I have also written here the high thermal and electrical conductivity of lithium, that can be explained in such a way. Now, if I talking about beryllium, okay, so what is the electronic configuration? Electronic configuration is 1s2, 2s2. Okay, so 2s is basically here valence shell. So here valence shell contain 2 electron. So if I am talking about beryllium 4, that means 4 beryllium atom will combine to form 2 BMO and 2 ABMO or anti-bonding molecular orbital. So each orbital, atomic orbital contain 2 electrons. So from 4 beryllium atoms, there will be 4 into 2, that is 8 electrons. So they are filled in this way: 1, 2, 3, 4, 5, 6 and 7, 8. So all the BMO and ABMO are electronically filled. Okay. So if I am talking about the 2s orbital, in this case, 2s band is completely electronically filled. Okay. So that is basically the valence band. So valence band may be partially filled or completely filled by the electron. So here 2s is the valence band is the 2s band, and that is completely filled by the electron. So above the 2s there must be a 2p band, as there are no electrons in the 2p orbital, so 2p band is basically vacant. So this is called conduction band. But in case of beryllium, it has been seen that the 2s band, this is the valence band, the filled 2s band and vacant 2p band are overlapped with each other. So there is a overlapping region. That's why by the application of very small amount of thermal energy or electrical energy, that is electron can easily promote from this valence band to conduction band, and that's why it can conduct electricity. Okay, so this also suitable for and can act as a electrical conductor. So not only beryllium, others alkaline earth metal, or not only lithium, others alkali metal also very much suitable for this for the conductivity of electricity. So now the how much amount of current is conducted or on the basis of on the value of electrical conductivity, the solid are classified into three categories. First one is the conductors. Conductor means the highest the valence bond is valence band is partially filled, or the conduction band and valence band are overlapping. So first one is the for alkali metals and the second one for alkaline earth metal. So in this case, I have already told you the forbidden energy gap, that is almost zero or zero. Okay, that's why they are very much good conductor for electricity. Their electrical conductivity value is 10 to the power 8 ohm inverse meter inverse. So those substances are called conductor. That is, like example, metals. If I am talking about insulator, in this substance, the energy gap, there is a forbidden energy gap. The energy gap between the valence band and conduction band is very high. It's almost greater than 3 electron volt. So electron cannot easily jump from valence band to conduction band. Okay, so here electrical conductivity is very less. So it is all about 10 to the power minus 20 ohm inverse meter inverse. For example, wood, plastic, rubber, etc. And another substance that is called semiconductor. In this case, the forbidden energy gap is not like conductor, that is zero, and not like insulator, that is greater than 3 electron volt. It lies in between 1 to 3 electron volt. So after applying some amount of thermal energy, or if you placed in an electrical potential, then it can conduct electricity, or by the transformation of electron from valence band to conduction band. But here also the value is obviously lower than that of conductor, that is 10 to the power minus 7 to 10 to the power 4 ohm inverse meter inverse. So the examples are germanium, silicon, metal oxide like Cu2O, CuO, etc. So there is a pictorial representation. In case of conductor, actually there is no forbidden gap. In case of insulator, there is a large forbidden gap, and in case of semiconductor, small forbidden gap. Okay. Now there is some difference. Conductor, that is the semiconductor, and the insulator. And what is intrinsic semiconductor, I will discuss later. So obviously I have already told you the in this case energy gap 0, in this case energy gap less than 3 electron volt, in this case greater than 3 electron volt. It is very high electrical conductivity, it is a moderate, and it is a very low conductivity. And there are some other points that are presented here. Okay, and if I am talking about temperature effect, so there is a something new. In case of actually, in case of conductor, with increasing temperature, electrical conductivity, that is basically decreased. Why decreased, I will discuss later. In case of semiconductor, with increasing temperature, electrical conductivity increases, and in case of insulator, the effect is very small. Okay, very small amount of conductivity increase. Okay. So there are some points that basically relate how conductor, semiconductor, and insulator are different from each other. Now we are basically interested about the semiconductor. We are basically interested about the semiconductor. Semiconductor are two types. One is intrinsic, another one is extrinsic. Okay. So intrinsic semiconductor means that this is a pure substance which conduct electricity, and this its conductivity must be lie between conductor and insulator, that I have already discussed. For example, pure germanium or silicon crystal. Okay, so in this case forbidden energy gap is small. After the application of thermal energy or electrical energy, electron can promote from valence from lower level to higher level, and some electricity electricity can flow. Okay, but in case of uh, extrinsic semiconductor, there is something new. In this case, to increase the electrical conductivity of any semiconductor, small amount of impurity is added to any intrinsic semiconductor. And this type of addition of impurity is called doping. So why doping take place? To increase the conductivity of any semiconductor. Okay. So depending on the nature of impurity, extensive semiconductor can be classified as N-type and P-type. Okay, so what is N-type, what is P-type, we have to discuss in detail. So first of all, there is an example like that. In this case, this is a semiconductor. Okay, this is a pure semiconductor. So in this case, actually, I have taken here silicon. So silicon has 4 valence electron. You all know that. So every silicon has 4 valence electron. Each valence electron form a covalent bond with the another valence electron of the neighboring silicon atom. So that's why in this way they form a silicon crystal. Okay, crystal. So at normal temperature, no issue, this bond is stable. But upon by thermal excitation, or if you applied small amount of thermal energy, or if you placed in electrical potential, then the incident happened that the electrons from this bond, this bond will collapse, and the electron is removed from this bond and go to the interstitial position. So there will be some vacancy. So there is a free electron, and the bond from where electron is removed, so there must be created a vacancy. Okay, this is a vacant position or a deficient of electron, and this is known as hole. In the language of chemistry, this is known as hole. So hole is created. Now to meet up this hole from another covalent bond, the electron will move in this position. So there is created another hole. To create this hole from another bond, electron will move this position, and in this way the movement of electrons and movement of hole, that's a take place. And due to this type of electron movement and electronic the transition of the electrons, so some electricity is generated. Now there is a function of this. It's in some cases the electrons are basically major charge carrier or majority carrier, and in some cases hole act as a major charge carrier. Okay, so how they are happened, we will discuss in detail. So at first I am talking about N-type semiconductor. So in case of N-type semiconductor, there is a silicon atom, that is we have taken a pure silicon atom that is doped with a group 15 pentavalent atom. So there is a phosphorus is a pentavalent atom. So in the crystal of silicon, a small amount of phosphorus are added as an impurity. So phosphorus has 5 valence electron. So between these 5 electrons, 4 electrons are combined with neighboring silicon atom, with the another electron of the neighboring silicon atom, and form 4 covalent bond. So obviously one electron is unbound. It does not participate in bond formation. So this electron is free, right? So this type of, so depending on the number of atoms of the impurity, for each from each atom one unbound electrons are there. So this electron can free to for the movement, and actually those electrons make a impurity donor level just below the conduction level. Suppose this is your valence band level, and this is your conduction band. Okay, this is a valence band and this is your conduction band. Now these electrons form a donor impurity donor level just below the conduction band. So what happened? With respect to this energy gap between valence band and conduction band, it is called basically forbidden energy gap. This is high. But this energy gap, that is the energy gap between the donor impurity level and the conduction band, is small. So electron, by the application of thermal, but in fact in presence of at room temperature, by the thermal excitation, the electron can move from this donor impurity donor level to conduction band, and due to this type of electronic movement, electricity generated. And actually in this case electron are majority charge carrier, so that's why this material is called n type semiconductor. N type semiconductor, negative or more as electron are in majority charge carrier, that's why it is called n type semiconductor. Okay, so n is related to the negative charge of the electron, you can imagine. Yes. Okay, so this is about n type semiconductor. Now, another is the p-type semiconductor. How p-type semiconductor work? Suppose there is a pure silicon atom, okay, that is semiconductor is doped with a group 13 element. Group 13 means boron, aluminium, that's a group 13 element. Suppose I doped with a boron atom. So boron is the trivalent. So in the valence shell, boron has 3 electrons. So in the valence shell of boron has 3 electrons. Okay, each valence electron of boron is tied to bond formation with the nearest valence electron of the silicon. So there will be the these 3 electron involved in 3 covalent bond formation with the another silicon atom, and these bonds are two center two electron bond. What is two center two electron bond? Between boron and silicon, that is a two atom, and between these two atoms there are two electrons are involved in the bond formation. So that's why this is called two center two electron bond. But here one another type of bond has been formed, that is called two center one electron bond, because in this bond silicon give one electron but boron has no electron, because three valence electron already involved in the bond formation. So there is a vacancy, so there is an electron deficient, so that is called hole, that I have already told you. Okay, now to meet up this hole, from the another two center two electron bond, one electron is go there. So there is a vacancy is created, so that is hole is generated. To meet up this hole, another electron from the two center two electron bond will move there. In such a way, there is a basically transfer of holes take place. And what happened in this case? In this case, there is a valence band and there is a conduction band. Obviously, due to energy gap is high, so electron, very small amount of electron can move from valence band to conduction band. But these holes basically create an impurity donor level, acceptor level, sorry, impurity acceptor level, because hole has no electrons, so it's a lack of electrons. So they actually create a impurity acceptor level over the valence band. So now this energy gap is comparatively low. So electron can easily move from valence band to impurity acceptor levels. Okay. So in the valence band, uh, there is a in the valence band, so number of electron will be less, because the electron will move towards the acceptor energy level. So in that case, the holes that are basically present in the valence band, that play an important role for carrying electricity upon applied of electric potential. Okay, so this hole is the basically majority charge carrier. Here the electricity is flow due to the hole. So hole is the majority charge carrier. So that's why this is called p-type semiconductor. You can assume that p is like positive, মানে lack of electrons. So that's why this type of semiconductors are called p-type semiconductor. So for n-type and p-type, in both case the energy gap will be reduced but will be less with respect to the with respect to the valence forbidden energy gap. That's why with respect to pure semiconductor, in case of n-type semiconductor and p-type semiconductor, the conductivity of electricity is high. Okay. Now the question is, what is the effect of temperature on the electrical conductivity on conductor, semiconductor and insulator? So you can expect that with increasing temperature, conductivity for each substance increase, but actually this incident does not take place. In case of conductor, if you increase the temperature, the atoms present in the crystal that are all vibrate, all will vibrate. Okay, so the electron, the free electron that is present inside the crystal, that which collide with the atom of the crystal, so there must be some scattering. That's why the speed or mobility of the electron will reduce. That's why electrical conductivity decrease, or you can say resistance increase. Okay, so that's why in case of conductor with increasing temperature, electrical conductivity decreases, or you can say have a positive temperature coefficient of resistance. In simple way, we can say resistivity increase, or obviously conductivity decrease. In case of semiconductor, there is a small energy gap. So if you increase the temperature, then more number of electrons, more hole will be increased, and obviously more electrons will be jump from the corresponding higher level, and electrical conductivity increase. So in case of semiconductor, with increasing temperature, electrical conductivity increases. But what about insulator? In case of insulator, the energy, the band gap, that is the forbidden energy gap, is very high. So if we increase the temperatures, very small amount of electron will move from lower level to higher level. So electrical conductivity increase only slightly. Very small amount of electrical conductivity increase with increasing temperature in case of insulator. So that's all the temperature effect for conductor, semiconductor and insulator. And those are the some application of semiconductor in case of diode formation, transistor formation, solar cell, laser diode, photodiode, sensor, etc. Thank you.